Good morning, good afternoon, good evening, everyone. Thank you so much for joining us for today's webinar. My name is Gerhard Golden. I work in the Global Industries Healthcare Marketing team at Dell Technologies. This webinar is one of a few webinars we scheduled as part of our efforts to take our HIMSS20 presence virtual. Today, Tizhoosh will present on image search for pan-cancer diagnostic imaging. This will be a 15 to 20 minute presentation with 5 to 10 minutes for questions at the end. If you have any questions during the presentation, please type them into the Zoom chat window as all attendees are muted. We will try to address as many of them as possible at the end. And now, without any further ado, I would like to introduce today's speaker, Tizhoosh. He is the director of the Kimia Lab at Waterloo University in Canada and an AI advisor to a Dell Technologies partner here on digital pathology. I will hand over to him right now, and he will put up his slides and start the conversation. So we're looking forward to a good presentation, and then we'll monitor the chat window for questions. Hamid, over to you.
Thanks, Gerard. Thanks, everybody, for being here today. So I want to go, as Gerard mentioned, in a 15 to 20 minutes presentation, give you an overview on image search. I hope everybody can see the slides. So as Gerard mentioned, I'm the director of Kimia Lab at the University of Waterloo, a member of Waterloo AI Institute, and a faculty affiliate to Vector. And at the present time, I'm also an AI advisor to Huron Digital Pathology. So microscopy has a long history. Everybody who is in the field or on the peripheral of the field knows that this technology has been around for several centuries in different forms. And it has even won Nobel Prizes for the people who are working in the field. And during the past decades, a lot of effort has gone into going from light microscopy to digital pathology. Usually we have a glass slide with biopsy samples on it after preparation. And the pathologist put it under the microscope and examine it, and then they write the reports and put the glass slides in some sort of archive, physical archive. Of course, you can put that glass slide in a digital scanner, and then you have a whole slide image from the entire biopsy sample. And then the entire repository of computer vision and, in recent years, machine learning would be available to work on those images. Of course, digital pathology has many key benefits. I just added more, so it's more than 4 key benefits. Of course, efficient workflows, connected teams, increased safety, telepathology, new insight from analyzing large data sets, and remote sign-in during crises like this, which of course is very important. There are a lot of studies that go on to whether there is a concordance between digital pathology and microscopes. I'm just showing one of them. Many papers have been published in that regard that show that the end result of light microscopy diagnosis and digital pathology are basically the same. So there is fundamentally no concern anymore in that regard. So the CAP, the College of American Pathologists, has some recommendations how to validate whole slide images among, to be able to adopt it within the clinics and hospitals. We just had a case that CMS relaxed the regulatory rules to help pathologists practice while working remotely due to the COVID-19. There is next week pajamas and pathology implementing remote sign-outs. It will be interesting to see what would be the impact of the pandemic on bringing the benefit of digital pathology to the attention of everybody, what will happen after the pandemic. So, of course, we are concerned with if you go digital now, what can you do with techniques like AI? What they can do for you? So, of course, you can classify images. This is yes and no. If there is a specific diagnosis in the question, lung cancer, adenocarcinoma, yes and no. You can train classifiers for that. You can generate images. One of the challenges we were experiencing in recent days was the lack of COVID-19 data sets that being available. So we can use AI to generate synthetic images. Of course, traditionally, segmenting structures in histopathology images is a conventional task. And our interest is search. You can search for similar structures in large archives. So whereas the first three are what we call supervised technologies, search is an inherently unsupervised technology, which means you don't need annotated data, you don't need labeled data, which means that technology can be applied on raw repositories available without any additional effort. So if you compare these two different approaches, so you can use AI software to classify histopathology data and yes and no, that's basically decision making, which means, okay, I want to take, in some cases, not in all cases, I want to take the decision away from the pathologist, but then the question would be, who should write the report? Whereas if you use the same AI software and re-function it to find similar cases, we are strengthening the position of the pathologist and enabling him to write better reports. So fundamentally the same set of questions, but employed in a different way. So one side, the emphasis is on decision-making, and the other one is on retrieval. So, and retrieval is fundamentally a pathologist-centric approach. A lot of concern whether AI can replace human experts. So if I give this thymoma specimen to a pathologist, I get a full report with a lot of details. If I give it to the AI at the current stage of the art, I get a word that says this is thymoma, yes. But there are many questions would stay open. Why, how, uncertainties, ambiguities. I need some measurements, any suggestion or recommendations. So at the moment, most AI technologies cannot do that. So the category of classifiers, in spite of their power and robustness for making accurate decisions, they cannot provide more information. So why search? Well, we usually have an archive that is being used to be searched with AI algorithm. This archive has been indexed, and then we can send query images and ask for similar cases, and we can get as many similar cases as the size of the repository allows. And of course, just getting the images back is not of no use to anybody. The important thing is that annotated data can also be retrieved, reports, follow-ups, treatment results, outcomes. That would make then the similar images very valuable, such that we can look at this as a virtual peer review. Pathology consultation has been there for quite some time. This is actually search. When a pathologist is looking at images, we definitely search in our brains for similar cases. We don't know how we do that as human beings, but definitely that happens. And we want to basically simulate that image search in human brain. So, but there is a lot of challenges to deal with. So one is that there is no labeled data generated in common workflow of pathology. Labeled data is like this quasi-circle around this tumor. So there is no such a thing in pathology. So because the doctors look at it and write the report, so there is no label. That's one challenge that you may have to deal with that. The other challenge is that images are very big. So they are in excess of several hundred megabytes. Easily they can go into 1 to 2 gigabytes depending on magnification and the size of the specimen. So, and people usually work on small patches like that, the one that Mark highlighted in that image on the right. So, and these patches of course are small. They can be 1,000 by 1,000 pixels. Other challenges that in the pathology that we are dealing with a huge diversity and the so-called polymorphism, that the same stuff, the same disease, the same abnormality can happen, can appear in very different ways. So that means we have a prohibitively large search space to deal with. So that's not easy. That's not easy for the techniques involved. So we have another problem is when we look at these images, the example of melanoma here is with 2.4 gigabyte of information. So how do you want to make computer understand this image is through, usually in computer vision, is through feature extraction. And which means for small patches, you calculate some numbers that computer understand as features or attributes. So for this case, for example, we calculated, so you get almost 180 megabytes of additional information features. And this is compared to 2.4 gigabyte, may not appear too much, but you still have to store this additional information. And no IT department in any hospital would like that you're asking for more storage, and also processing 180 megabyte of information additionally for every whole slide image would be a huge challenge. So our fundamental idea is the content barcoding, so which means we get those patches when we convert them through barcodes. They are not conventional barcodes that we see in grocery, they are what we call deep barcodes. And if you get those barcodes, basically if you look at this lung adenocarcinoma case, you can grab a proper suitable number and positions of patches. And so instead of working with the image, you represent the whole slide image, the biopsy sample, as bunch of barcodes, that as we call it. So, and then now, instead of working with the pixel information, you are just operating on barcodes, zeros and ones, black and white, which is very fast in any computing platform. So the deep barcodes that we calculate, so you put images through some sort of deep networks. We don't care about the output. We grab some information from inside. Many people do that, but we convert that information to barcodes to represent those patches in whole slide image. So how we can search? One, you can search for whole slide image, which would be the ultimate challenge. How can I search and compare gigantic images? But if you are using barcode, that's not a challenge anymore. We can search for patches or tiles. So these tiles could be as small as 1,000 by 1,000 pixel, or even smaller if necessary for certain diagnostic applications. Or you can search for regions, depending on what the pathologist is interested to do. So why AI and image search? So fundamentally what we want is virtual peer review, so that if the pathologist is looking at that image, he or she sends the whole slide image to an image search engine. The image search engine goes inside a large index archive and finds similar cases. Here, the top 3 that we are showing that are similar. That means they have similar morphology of the tissue. And at the same time, you also retrieve the reports for those cases. So, of course, when we look at that, the image came from a specific pathologist, but the images that we retrieve come from different pathologists. So we are accessing the knowledge and the evidently diagnosed knowledge of the cases that are in the archive. At the moment, that information is not being used. So if you have a query whole slide image that a pathologist is looking at, and you use search, you get top N search results. So we are showing here top 3. You may get top 5, top 10, top 50, top 100, depending on the size and the diversity and heterogeneity of your archive. And depending on that, you can build what we call a computational consensus. So here, for example, papillary thyroid carcinoma, which is not a difficult task, difficult diagnostic case to begin with, but you can build a diagnostic consensus. So if you do that, then you have the search engine. Here I'm showing the demo that Huron Digital Pathology demos in different exhibitions. So on the left-hand side, you see the thumbnail of similar one. Then you see the query slide, patient 0046. And on the right-hand side, you see the similar slide, patient 0063, together with the report. So side by side, the pathology can look at what the patient, the new patient who has not been diagnosed yet, and the most similar patient on the right-hand side, plus the report, which is as if you are basically showing your image to your colleague and say, what do you think? And the Dr. Jones here is telling you, this is this is that, this is small cell glioblastoma multiforme, and so on. So this is the power of image search for pathology, because then this is within the category of explainable AI, that the decision can be justified if you say this is similar to this, and then you can use the information in the pathology reports. Of course, there is a lot of information in the pathology reports. So here, just a simple example, you can break it down into topics, you can break it down in keywords. You can, when you show this report here, you can go and highlight specific reports upon request, because you don't want to bias the pathologist. But we know the natural language processing is one of the oldest branches of AI. There's a lot of capable technologies available, and we can use that to combine it with the power of visual search. So what we did, we wanted to do a full-scale validation, so we went used the National Cancer Institute TCGA dataset or genomic data common portals, and did a validation on 25 organs and 33 type of subtypes of cancer. So we looked at 30,000 whole-slide images, around 16 terabyte in compressed form. We processed 29,000 of them at 20 times magnification. So almost 17,000 were frozen sections, and almost 12,000 were diagnostic slides. So we processed 20 million patches, each 1,000 by 1,000 pixel, to assemble index all images to be able to search. So working with the big data, so it has its challenges. So the approach that we use, we look at those whole slide images and find patches that are relevant to represent the polymorphism of the tissue. And we grab those patches and we assemble, we construct something that we call a mosaic. So here, a mosaic sample for the image on the left, and 3 of them have been randomly selected. And then we convert that mosaic to barcodes. So this is what we call a bunch of barcodes, or BOB. And those 3 with green, blue, and red, so we can take them out to look at them. So this is just look like some binary information that doesn't make sense to us as humans, but is good for computer. So the BOB, or that bunch of barcodes, 60, 70 barcodes here are representing that whole slide image on the left, which is around 1 gigabyte of information. You can put it in 15 kilobyte. So this is now, you can start and search. So example for patch search, you see on the left the query images, so the images as input, and then you see the images that the software has found as similar, from simple structures like fat and hemorrhage to different types of epithelium. You see examples that visually the software can go and find similar cases, but you have to quantify it somehow. So what we did the so-called horizontal search. So when you provide an image of lung, breast, kidney, brain, we search an entire data set repository of 30,000 whole slide images as if we don't know what it is, as if we don't know it is a long image, because we wanted to know that the software can recognize it. And you see the diagonal of this heat map is pretty occupied, which means if we searched for brain, we found brain. If we searched for breast, we found breast, and so on. So horizontal search is just a sanity check to make sure that the search is working. We came up with the chart, the core diagram for this. Everywhere that you see colored, solid colored, it means we found the proper one. And there is a lot of connections in the middle, interesting connections that have to be investigated. That could be horizons for discovery. If I'm searching for prostate and I find lung, that could be interesting to look at. If you zoom in at 20x, you see that's adenocarcinoma. Of course, if you search for prostate adenocarcinoma at 20x, you may find lung adenocarcinoma. But there are other things that we have to look at it. So we have no previous work to look at the core diagram, the connections between different type of cancer. This is something classification techniques cannot do. This is something that is the domain for image search. So, and then we did vertical search, which means you give me an image and I know it's breast image, kidney image, and only search within that primary site. I restrict the search within that organ and nothing else. And then we expect that if I'm looking for low-grade glioma in brain, you have to find me low-grade glioma cases because I want to confirm a potential diagnosis. So we did that. We did a lot of experiments. In many cases, we got really high values, 91% accuracy, 98% accuracy, and so on. But sometimes we also got really low values, 58, 33%, and so on. And you can see it also in majority 15 and majority 20, top 15 and top 20, that sometimes we had 0% accuracy, sometimes we had 100% accuracy. The reason for that is it depends on the size of the archive. So if you have only, let's say, 43 patients, your accuracy will drop if you continue to retrieve more and more images. If you have 178 patients, even if you go top 20, top 30, top 40, you stay quite accurate, close to 100%. The same way for kidney and bladder images. So if you have around 500, you are quite accurate. If you have less than 200, let's say less than 300, you may not be as accurate. So the data was telling us you need a large archive to be able to be accurate. So what we learned from that validation is the more the better. So we saw a positive correlation of 80% between number of patients on one side and the accuracy of the majority consensus on the other side. So we also learned that quality of the data matters. So 40x seems to be better than 20x. You may need the stain normalization, and artifacts may disturb whatever it is that you are doing. But more importantly, we found that building diagnostic consensus with high confidence is possible. For frozen sections, we had 93% accuracy for bladder, 97% accuracy for kidney, ovarian 99%. For diagnostic slides, we had example prostate 98, sarcoma 99, thymoma 100%. So there were some numbers that we went back with double check and triple check because the numbers were scary. If you get 100%, you have to make sure that this is not a bug. But when you're searching in a database of 30,000 patients and samples and 20 million patches, the likelihood that you hit it randomly is quite low. So there is something there in search that we have to exploit. So Lagotto is a commercial product that Huron Digital Pathology is pushing into the market soon that is capitalizing exactly on this technology to enable the pathologists to search in the archive of hospitals, clinics, and maybe even regional ones. How do we want to do this? Because it needs some infrastructure. If you have a digital scanner and you're accessing a GPU server to index your images, and then you need some viewers, some PACS viewers through API to look at the images and write your reports, and then the pathologist can do its work, and that viewer has connection with the LIS, with the lab information system. The technology is agnostic toward the scanner. So if your scanner is not from Huron, so because Huron is using the Isilon server to store the images and communicate with power a GPU server, I'm doing the same thing in my lab at Kimia Lab. So we have both Isilon server and Dell EMC GPU server to be able to have high performance storage plus enough computational power. If you're using other scanners, it doesn't matter because as long as the technology can read the images, they can be indexed and searched. So there are some publications. One is on the left, is not peer reviewed yet, is under review with a medical journal, Utixel, an image search engine for large archives of histopathology images, which describes the technology that will come out soon, hopefully after the review is done. On the right, you see something that already has been published with the Nature Digital Medicine Partner Journal, Pan-Cancer Diagnostic Consensus, which exactly reports what I briefly described with the validation that we have done with the 30,000 WSIs from TCGA. So this hopefully is a brief overview of what image search can do here. Organizations that support us, Ontario government has funded us for the next 6 years. Huron Digital Pathology is our sponsor. Dell EMC is our partner and mentor, who has helped us to figure out the storage and computational power. And many other institutions, as you see, UHN Vector Institute, Grand River, NSERC, UPMC, and MITAX, and many others that I may have missed to mention. Thank you very much for your attention. I would be glad to take any question if possible.
Hey, Hamid, thank you so much for that. That was really good. It was a good overview of the benefits of how sufficiently large databases of searchable cancer subtype cases can help to automate diagnoses via virtual peer review and other virtual settings. You know, there's so much of that, you know, that's the talk of the town right now with telehealth and virtual visits, and also with the DPA announcement that some of the pathologists can now, you know, be reimbursed for remote work. I think this is a huge, it was a really good presentation to show some of the benefits of AI and how large databases can help with that. So we will go ahead and take some time now for questions. As a reminder, please be sure to type your questions into the question box in the Zoom chat window. As you're all on mute, then I can relay the question to Hamid. But in the meantime, we already have 2 questions coming from Patrick Miles. So I'm going to ask Patrick to ask those questions.
Hi, thank you, Gerhard. Hi, Hamid. Maybe talk about some of the insights that have surprised you in both the development and the validation of this technology. Like, what's really surprised you from the feedback?
Well, one of the surprising points was that in spite of all the hope and academic and empirical knowledge that the entire AI community has, we were not expecting to come even close to those high accuracy values with the TCGA data. Everybody in the field knows that the TCGA data set is not a perfect data set, but is the only large publicly available data set that we have. People, our colleagues, are working to come up with an improved version of that, and we will test again. But it seems, because we have been working in the field for quite some time, that always accompanied with a healthy portion of skepticism, and image search and retrieval has been around for more than 2.5, 3 decades, and a lot of failures and disappointments. I was really surprised toward the end of last summer that after the implementation and initial tests with really small data sets, when we went online and tested with millions of patches, we could relatively easily hit those high values. That was a surprise, and we went several times back and said, how are we getting 100% for thymoma? Why we are getting 99% for ovarian cancer? This could be a bug. Test again, test again. It was a surprise, but it seems the technology is ripe. We have the technology, we can do it. Of course, we have to put it in place, we have to test it, we have to validate it. And this is not the end of the validations that we do. This is just the beginning. We have to validate more. But again, for such a data set, the surprise was that such high accuracies through combining the majority vote of top search results is possible. That was a big surprise.
Patrick, did that answer your question?
Yes, it did. Thank you.
I see there's a question here. Can we have a link to the recorded lecture afterwards? Absolutely. We will highlight the link where it will be posted at the end of this call, and I'll put it in the chat window as well. Are there any other questions right now? I'm looking at the chat box. I'm not seeing more questions. I know we're coming up on time here in any case. Just double checking one more time. Yeah, I don't see anything. So with that, Hamid, did you want to share anything else before we end the call?
Well, no, we are just going around and asking different clinics, hospitals, and pathologists if they have data that they can share, such that we want to build a larger repository of validation cases. So hospitals, we can go there and validate. They don't need to share the data beyond the firewall of the hospital. It's extremely important that we test and validate this technology for larger archives of clinical data with access to annotated information. And again, it doesn't need to, the data doesn't need to leave the hospital. So any clinic and hospital who's willing to partner and collaborate and support us with validation, that would be highly appreciated. Again, we can come in and test. You don't need to really be worried about the privacy of the data.
That's a great request. So Hamid, while I'm wrapping up here, if you don't mind putting in the contact information where you want people to send this information in the chat window for everyone to see, that'd be great, or Patrick. And then I will do the same thing with our site, but I think that's a good request. So if there's anybody on here and you want to get in touch with Hamid, he will put his contact information in the chat window right now. So from Dell Technologies perspective, thank you so much, everyone. We appreciate you being here. Please note that this webinar was recorded, because that was one of the questions, and it will be posted on our virtual HIMSS20 website, which is delltechnologies.com/HIMSS20. pathogenetician.com/HIMSS20. And this site will be continually updated with future customer webinars, social meetups, our recorded technical demonstrations, and then other content. And those technical demonstrations do actually include the Huron digital pathology solution that was highlighted here. So please bookmark delltechnologies.com/HIMSS20 and check back regularly for new content. Thanks again for joining us today, and please stay safe. And with that, it's the end of the webinar, so you can log off.